Let's talk about work for a minute. So this is the other method for transferring energy that we are going to talk about in this chapter. We've been spending most of the chapter on heat, and truthfully we'll spend most of the rest of this chapter on heat as well. But we're going to talk about work now for just a little bit. And we're going to look at one specific kind of work, because there are actually, in reality, many different types or versions of work that can be done. We are going to be looking at what's called pressure volume work. This is when you have a gas that is under a constant pressure and either expands against that pressure, which would then be doing work on the surroundings in that case. If the gas was our system, it would be doing work on the surroundings, or it gets compressed by that pressure, and so then it's having work done to it. So, as it states here, when the gas expands, delta V is positive, but the system is doing work on the surroundings, so the work that is done by the gas is actually negative. So again, that's what I was just saying there. If the gas is expanding, it's pushing out against the surroundings, and so it is doing work, which means that it has negative work values. And if the gas is being compressed, if it's being squashed down, that means the surroundings are doing work to our system. And again, this is assuming that the gas is our system, which is always going to be the case for these types of situations. So the equation to quantify the work that's being done here is thankfully very straightforward. And by the way, here, this is a bullet point. That's not a negative sign. This is a negative sign here. So the work that's being done is equal to negative the pressure times the change in the volume. And the units here and the directionality are going to work themselves out using this equation here. So we don't have to worry about like we did before with the heat, as to whether the heat is going into or out of our system. Because we are talking specifically about a gas, we're kind of restricted in terms of what our system can be. The gas essentially has to be our system, and so we don't really have to worry about into or out of. If we're describing the change in volume of the gas, this equation will tell us whether the gas is either doing work or is having work done on it. And that will all come from this delta V, whether delta V is positive or negative. Alright, if we're going to take this work value, by the way, and convert it into a more usable unit, because if you notice here, the unit for pressure, which we haven't gotten to yet, it's in the next chapter, actually, but the unit for pressure is atmospheres, and then the unit for the change in volume would be liters, which gives us units of atmospheres times liters, which is a very strange combination of units, but it is in fact a unit of energy, a liter atmosphere. We would like to use joules instead, though, and so we have a conversion factor here for us to use to convert from liter atmospheres into joules. So 1 liter atmosphere is the same as 101.3 joules. So let's look at an example real quickly. To inflate a balloon, you must do pressure volume work on the surroundings. If you inflate a balloon from a volume of 0.1 liters to 1.85 liters against an external pressure of 1 atmosphere, how much work is done in joules? So, because we're asked about pressure volume work, you should automatically think of this equation. Oops. Starting to do the volume first, so it's a delta V there. Sorry for my sloppy writing there. Just do that over. Okay. Delta V. There we go. So the work is equal to negative P delta V. Pressure is just given to us in the problem. It's 1 atmosphere. Delta V is also given to us, but it's given to us in the form of an initial and a final pressure. Now remember, delta anything is always going to be final minus initial. So the final volume in this case is 1.85 atmospheres, and the initial volume is 0.1. So that gives us a delta V of 1.75. Sorry, why did I put atmospheres there? Liters. Sorry about that. Okay, so 1.75 liters. So we, at this point, have everything we need. That's it. So if we go ahead and plug in what we know, the work is equal to negative 1 atmosphere times 1.75. I started to do it again. I don't know why, but my brain wants to write atmospheres really badly. 1.75 liters, which gives us negative 1.75 liter atmospheres. But the question does specifically ask us to give the work that is done in joules. So we have one last thing to do here. We have negative 1.75 liter atmospheres. We need to convert that into joules. And if you check back here, 101.3 joules is the same as 1 liter atmosphere. And so if we do that math, we will get negative 177.3, essentially, joules. Struggling with the units in this problem for some question. Just started to write liter atmospheres again. Anyway, so negative 177 joules. If we think about the sign for the work here, it makes sense. We have a balloon, the gas inside the balloon, based on the sign that we're given, is doing work on the surroundings. Because if you remember, a negative work means that your system is doing work on the surroundings. And that makes sense because the gas that is inside the balloon, as it is expanding, as it's expanding the balloon, has to push the atmosphere out of the way. Because there is atmosphere all around the balloon, and so as you're pushing the air into the balloon, as you're blowing the balloon up, the gas that's inside of there has to push the atmosphere that's around the balloon out of the way so that it can occupy a larger volume. And so it is doing work to the surroundings. And so this unit, or this sign, makes sense, having a negative sign. All right, so then this gives us our two ways to quantify how much work, how much energy is either being put into or taken out of our system. We have a way for quantifying the heat that is moving, and we have a way of quantifying at least one form of the work that is either being done to or being done by our system. So these will come very handy for us. One quick thing before I finish up this video here. I do want to mention bomb calorimetry, just because it is a topic that's discussed in the book, and it is a very useful instrument, the bomb calorimeter. It's not nearly intense as it sounds. It sounds like something out of a sci-fi movie, but it is very cool and it is very useful, but having the word bomb in there makes it sound much more exciting than it actually is. Essentially what a bomb calorimeter does is it allows you to determine the caloric content of materials. It's most often used for foods, but it doesn't have to be used for foods. You could do it for essentially anything that burns. You could use bomb calorimetry to determine the caloric content in terms of food, but also even the enthalpy, which we'll talk about in just a second, of other materials. And the way that you do this is you place a known amount of the material that you're working with. So let's say you're determining the caloric content of a gummy bear, which I actually did when I was an undergrad in school. I determined the caloric content of a gummy bear and a Lifesaver mint. I actually don't remember how accurate my calculations were, but we did that in the lab, and it was pretty cool. So you take a known amount of a material, and you put it inside this container that's called a bomb, and you flood the bomb with oxygen gas. And what the oxygen gas does is it makes it, the stuff inside of there, burn very, very, very well, very efficiently and very quickly. It doesn't burn instantaneously, though. You do have to provide a spark, and you provide the spark with these ignition wires here at the top. So you have the sample in here that can burn. You have pure oxygen inside of there, and when you're ready, you light the inside, and the oxygen gas causes everything inside of there to burn up completely. When it does that, the heat that's released goes into the water that's around the calorimeter here. And as that water heats up, you measure the temperature change, and you know exactly how much water is in here. So you know exactly how much water is present. You measure exactly how much the water heats up, and because you know exactly how much material you started with, you're actually able to essentially work backwards from the amount of heat that the water absorbed to figuring out how many calories of energy that food had to begin with. And so you can work out the caloric content of that food. So in a nutshell, that is how a bomb calorimeter works. And hopefully the YouTube algorithm does not cause this video to become restricted because I've said the word bomb so many times. Don't take my video down, YouTube. I'm just talking science here. Anyway, that is it for this video. I will see you all in the next one, where we will begin our discussion of enthalpy, which is really the last main topic of this chapter, is enthalpy and enthalpy changes. So I'll see you there.